All right, guys, I'm Nicolette, and today Brian and I are here with Greg Ducharme, Product Director over at Laird Thermal, and Vineet Barot, Technical Support Manager of Thermal Products over at Sager Electronics, to talk about liquid cooling. So if you happen to think liquid cooling is an issue, it may not be as big of an issue as you think, and we're going to explore that topic today. So thank you both for joining us. We appreciate your time.
Sure, of
Yeah, no
course.
problem.
So why don't we kick off with a little bit of an overview and an outlook of the market? Let's really talk about some of the factors that are expected to drive market development, maybe even the current state of liquid cooling systems in the industry. Where do we stand on that, Greg?
Yeah, sure. So liquid cooling has been a growing market for decades now. Heat densities, are always going up. So this is a result of equipment, instruments getting smaller and smaller and becoming more and more powerful. Decades ago, air cooling was sufficient for a number of applications. It no longer is. Companies are starting to rely on liquid cooling more and more. And this comes in a whole different, a variety of fashions in terms of how they're actually cooling the liquid that's being used to cool their instrument. But all in all, the markets around cooling in general are growing, I wouldn't say exponentially, but quite significantly. And liquid cooling is no different than those.
So what are some of the applications that we see?
Yeah. The bulk of the applications are in the industrial and analytical space. There's some other applications in medical, but the bulk of the business is at least where Laird Thermal participates is in industrial and in analytical. There's a number of other applications, whether it be military, aerospace, consumer type of products. But when we think of equipment that's really generating a lot, consuming a lot of power, generating a lot of waste heat. These are in some of the industrial processes. Lasers are a real good example of equipment that require cooling. And when you look at the efficiency of lasers, a lot of the input power is then only a limited amount of it is converted into actual laser power. And so the rest of that needs to be cooled somehow. And so obviously the bigger the laser that gets, the more cooling that's required. There's a number of applications within the analytical space that require liquid cooling, but maybe not so much from a bulk heat removal perspective. They're more looking at thermal stability. So when you think about all these very precise instruments that are trying to generate data for analysis, whether it be a mass spectrometer, electron microscopes, these require real precise operating environments in order to give precise results.
Now, what about chillers? Are there different types of chillers?
Yeah, so in the liquid cooling world in general, there's a relationship really between the amount of heat that needs to be cooled and at what temperature it needs to be cooled at, right? So obviously, the more heat you start rejecting, the more energy that needs to be transferred away from the equipment, we tend to gravitate towards liquid cooling. And then as the set points become lower and lower, we gravitate towards chillers. So chillers is kind of the industry term for cooling systems that use, I'd say majority of the time they use refrigerants, but I guess it's referring to cooling below ambient temperatures. So when we're talking about above ambient temperatures, it tends to be more of a bulk heat removal application. And so the best example in terms of liquid cooling of that is an X-ray tube. X-ray tubes are notoriously inefficient, and so there's a lot of heat being rejected. But they're not really concerned with precise temperature control. They're more concerned with just keeping the tube from getting to a point where it's going to fail, a critical temperature. So with chillers in general, we get into both of these, right? We're trying to transfer heat, but we're oftentimes trying to maintain a precise temperature. And so the technology itself, we can go, they tend to start showing up in applications of I'd say around a kilowatt, oftentimes lower than that, but say a kilowatt, and they can get up to very, very large systems that are facility systems, located on rooftops and whatnot. And so there's different players in the market that make different types of chillers, primarily based on sizes, right? So some companies will, like Laird, we focus in kind of the single digit kilowatt cooling capacity, and then you get up into tens and hundreds of kilowatts, which is a completely different animal.
Yeah, I would say even just describing that ladder you're talking about, starting from air cooling, right, is we're talking about going from air cooling to liquid cooling, and there's kind of a chasm there. We can talk about how to get past that. But even in liquid cooling, by the way, the reason why liquid cooling is already so much better than air cooling is because water just has a much better conductivity than air. So that's the reason to go to liquid cooling in the first place. Then once you introduce water into the system, the question is, well, how do I cool this water, right? Because unlike air, it's not freely available everywhere. Right. So you have to process it. You have to cool it back down after you heat it. You can do it in a way, if for example, whatever you're cooling doesn't need to be below ambient, like Greg was saying, you can do it with like a heat exchanger or something like that. Mm-hmm. But for a lot of applications, you want to go at ambient or below, or even just you want really tight temperature control. And so having a packaged system like a chiller is a way to really accelerate that process and give you something neat and clean.
So with all that, right? We see a little bit of hesitations from companies going from air to liquid cooling. Why do you think that is? If it's more efficient?
Can I just ask one question? Mm-hmm. Is there a difference between a recirculating chiller and a regular chiller?
No. The quick answer
okay.
is
I just wanted to make sure. Okay, go ahead.
Yeah, I think it's probably just differences between the industries. So I've
heard recirculating chiller to mean not below ambient as one kind of modality there. So it's like if it doesn't have a compressor, it doesn't have a Peltier.
Okay.
If really it's a packaging of a pump and a heat exchanger and a fan and everything in one place. But in a way, everything is a recirculating chiller because it's a recirculating loop. So it's sort of a misnomer.
You can get into flow. I mean, this is a detail, but you can get into flow through chillers. If you think of a water fountain that has a refrigeration system in it that's cooling the water, and that's not, thankfully, recirculating. Right. So they also have those in industry as well, where it wouldn't have its own pump, and it would be chilling tap water or something like that.
Right, and it'd be passing out, and that was it, and then not coming
Before
back.
we went any further, I needed to just clarify.
All right,
that.
Thank
you.
Vineet was so deep into talking about the differences, starting to go into air. So I was like, well, why? Hey.
Yeah, I know. I was like, wait a second, I don't understand something. Hold on.
It's honestly, that's why I think it's easier to talk about specifically what is it that you're trying to do, and also what is the technology you need to get there, rather than like the words, which different people use different terms and words.
Okay, thank you for clarifying. I'm sorry, Brian. Go ahead.
That's okay. So my question, Vineet, was considering how liquid cooling is so much more efficient, there is some hesitation for certain companies to switch over from air to liquid. Why do you think that is?
Well, it's a totally different system, right? So if you're used to making electronic boxes with fans in them, with maybe some sort of air exchange unit in them, you might put heat sinks on certain components that get really hot. That's a totally different system from saying, okay, now you need a cold plate, you need liquid fittings, you need these connections. And so, and even mentally, there's a whole shift of, okay, how do we handle leaks in our system? What kind of fittings do we need to get so that we lower pressure drop? But at the same time, maybe we need quick disconnect. So some folks might need to disconnect a line really quickly to work on it and connect it back with zero spill. So it's just a whole different regime. But honestly, it's for a lot of customers, for a lot of applications, it can keep them from getting to that next step. So if they might be throttling their power, they might be throttling their features because air cooling is just not enough. And this is where there's a little bit of learning curve, but this is where Greg and I are here to help, and help them through that process.
Right. I mean, companies don't. It's rare that someone goes to liquid cooling just because they want to go to liquid cooling. A lot of companies will avoid it. I don't want to say at all costs, but they put it off as long as they can because it brings a level of complexity, as Vineet had said. So complexity and I guess you could even say risk, right? I mean, electronics and water don't mix too well, and so there's always someone there that's concerned with that, taking that step.
Well then, all right. So let's say a company does make this jump, right? They're ready to take a leap. How do they determine now which product is right for them?
Yeah. So so for starters, that's where we help out. You need to think of it as a complete system, right? As Vineet was talking about before, there's always I would say at least two heat exchangers in the thermal system. So one is in the OEM or the customer's instrument. So they're somehow transferring heat into a liquid here in this case. And so then what we want to do is how do we take that liquid and reject it elsewhere? Well, they've designed this heat exchanger in their piece of equipment to function with a given set of parameters, right? They have so much heat they want to transfer, and they're doing this with a certain flow rate of a fluid at a certain temperature. And so those are the kind of the basis of input into any kind of cooling system. How much heat, what's the flow, and what's the temperature? And so as long as a cooling system is providing them those specifications on an ongoing case, their system's going to work. So then we design a heat exchanger on our side, depending upon those inputs. So the first question is, are we operating above or below ambient temperature, right? And that drives the system towards a refrigeration-based system or not. Beyond that, we start talking about some of the details. What kind of pressure do you need? What kind of controls do you need? And so there's oftentimes these are standalone systems. So there's a wide variety to choose from in the industry. There's a number of companies out there that are making this type of technology, all kind of focusing on different markets, right? I mean, the company that's supplying a chiller to a welding machine is different than who's supplying one into for a piece of analytical equipment. They have different focuses. There's different cost points, different features, all of that. And so, but we take those inputs and we've based on a lot of our experience in the market, we've developed our own standard system. Now, Laird can manage the smaller capacities with Peltier thermoelectric coolers, and then when we get into higher heat loads, we can do it with refrigerated systems.
So let's address some of the common questions that people may have, right, and even think they know the answer to sometimes. So Vineet, how easy is a liquid cooling system, specifically chillers?
Chillers themselves are super easy. I mean, a lot of the stuff like Laird has, they're very user-friendly, easy interfaces. You plug in a temperature set point, and there's more advanced things like alarms and things like that. But as somebody who's used chillers for many years in different labs and things like that, the good ones, it's easy. You turn it on and you say, I want my liquid at 22 degrees, and you get your liquid at 22 degrees. So that part itself is super easy, definitely. And some of the selection that you were talking about earlier, like how do I know which chiller to use, is because of those features. You might want better features or bells and whistles. But at the initial level, when I'm talking to customers, it's more just, okay, it's 2 kilowatts of cooling. You need this temperature. Okay, here's roughly the chiller you need, and for budgetary purposes when they're thinking about what to do. And then it gets into the more details, like Greg was saying.
So what are the base sort of pieces of information they need to get started, right? Like you mentioned, like temperature, things like that, or features. Like what do they need to know when they come and say, okay, I'm gonna look for a chiller?
Yeah, it's the amount of heat that your cold plates and whatever your process is drawing, what temperature you need to keep it at, what's the maximum ambient temperature you expect the system to be in, whether it's indoors, which is a lot of these applications, or maybe it's outdoors. That'll get you most of the way there on the thermal side. Greg, what are some other ones?
Yeah, you can. It's like buying a car, right? There's all kinds of options and features, and a lot of these products have really become configurable in the market. So if you want to have a filter added on, or if you want to have the ability to control different flow rates, or and a lot of companies have different product lines to service different markets, and so it's really you can really get into the details of what it is you really want. And there's different buying practices out there too. Whether or not the person that's buying the product is actually going to be using the product. So there's a big differentiation there. A lot of the OEMs aren't as concerned with the features, right? They're not selling more of their product because it's got a nice chiller, right? So they want to have low cost, and they want to have the minimum features, something that's reliable, it's going to work. But then on the other hand, when the user is actually making the purchase, they're more apt to look at some of the features, what's going to really might be lower energy consumption, or it might have a easier to interface with display. All of these features, really, they can get into those details. So yeah, it's really different depending upon who the buyer is.
Okay, here's a question. Are chillers loud?
The noise is always a concern with chillers. And it's really, it's related to how much cooling capacity. So you could say yes, that they can be loud, but then the smaller they are, the less noise they're making, right?
Okay.
The majority of the noise is coming from air movement. And so when we're rejecting heat into the local room with a heat exchanger that's using air, the more heat we're rejecting, the more airflow we're moving, the louder it gets, right? And so but there's been a lot of advances lately, I would say over the last 10 years, to really reduce the noise of these systems. So higher efficiency heat exchangers result in less airflow, and that makes the unit a little bit quieter as well. And and the big reason that the noise has become an issue is because if you think of a laboratory environment, they're taking this chiller and cooling a piece of analytical equipment, and the chiller is located. It can be within a couple of feet, couple of meters of where the work is being done, and so no one really wants to work in a loud environment. But of course, when you get into larger systems, more air movement becomes more noise. But you reach some point where these big chillers can no longer be installed indoors, right? You can't start taxing the HVAC system with 20 kilowatts of heat and all this air moving around. So then that becomes an outdoor or rooftop unit. So, but noise is definitely a focus these days.
So what's the difference between a portable and a fixed chiller?
Yeah, the easiest way to answer that is probably a portable has wheels on it, right? And all of these systems can be, they need to be moved to be installed. Obviously, a rooftop system tends to be more fixed, and any outdoor unit tends to be a fixed unit. But a lot of these systems find their way into a single installation site. Even the ones that we call portable, they have wheels on them, but they're more or less used for ease of installation, right? You want to roll the system out of the shipping box and put it into its installation site, and it'll stay there for years. Is what tends to happen in the market. But there's always they can be used for many different applications. So.
Okay, so I have a question. You mentioned outdoor chillers and indoor chillers, right? What's the benefit, right, with the outdoor versus indoor? Because you also talked about like taxing like an HVAC system. So is there much more benefit from that perspective if you have an outdoor chiller or like a rooftop unit?
Yeah, it's really into the heat loads. So when you get into large heat loads, if you think of take a hospital, for example, they've got dozens, if not hundreds, of different systems within the hospital that require some type of cooling. And what they do is they put in a central facility system with an outdoor chiller, as opposed to putting a small cooling system in every single room that's cooling the piece of equipment. So it's largely driven by the amount of cooling that's being done, and then it's also being driven by how the facility is the facility is structured.
Gotcha.
Data centers are another great example, right? They tend to have a central system that's then feeding all of these other heat loads that are within the facility.
Okay.
Yeah, I did want to talk about the noise thing, by the way. One thing on the positive side of liquid cooling, anybody who's done a liquid cooled CPU desktop versus a air cooled knows the liquid cooled is actually quieter, right? And so there, the line we talked about going from air cooling to liquid cooling. If you're talking about cooling at very high densities where it's getting to the edge of air cooling, which is around 0.1 degrees C per watt, those are very, very loud fans. You don't want to be anywhere near them. And if you switch to liquid cooling there, you'll end up with a chiller that's pretty small and pretty quiet. Now, noise isn't the only issue in a lot of applications, so there's tons of considerations, but there are cases where going to liquid cooling and chillers is actually quieter than air cooling.
Yeah, a lot of that's there's beyond the actual noise. I mean, so Vineet had mentioned about the thermal properties of air versus water. There's also physical properties, so density. When you start looking at mass flow rates of air versus water and how much energy they can absorb per degree Celsius or Fahrenheit, it's really quite a huge, very large difference. And so noise is one of the items. And then also when you start talking about being able to transfer that heat away from the application, you're talking about ducts that need to be very large, whereas liquid can pass through very small tubes and be sent back and forth to the application with very little impact in terms of the installation site.
So how does service work, right? How does servicing a chiller work?
Yeah, so think of a chiller like your refrigerator at home, right? You buy a refrigerator and you expect it to work for, let's say, a minimum of 10 years, right? A lot of the same types of components in there. So the refrigeration system is virtually identical: compressor, heat exchangers, some valves to control refrigerant flow. Electronics have become very reliable these days. And then beyond that, it's a fluid system. So the pump tends to be the critical part of the entire system. So pumps oftentimes have mechanical seals, and these seals can fail in time. So pumps would often, I would say, would be the part that needs service. So maybe it's every 5 years, or maybe it's 10 years. Some companies are preventative about this in terms of replacing it before the failure, and then others will do it after. But beyond the pump, it's in a lot of those pump failures, quite honestly, result from fluid quality problems. So customers not maintaining the fluid quality. So when we start talking about the use of water, we can get organic bacteria growth, algae growth in the fluid. That starts gumming up the seals, and then next thing you know, there's a leak. So that's probably the best thing that a user can do for their chiller, is to maintain it, is by replacing the fluid in the system, just like you would do with your automobile, right? There's you would replace the fluid every so frequently, and that's one of the big.
They're pretty self-sufficient,
Sure. Yeah, it all depends on the type of system you have. We purposely at Laird designed the fluid system so that we call it a semi-closed system, and it's very similar to your automobile. So it's sealed off, and the only time it opens to the environment around it is when there's a pressure buildup. And so what that does is it prevents a lot of the any kind of growth from or bacteria passing into the fluid system. And I mentioned it's the same as changing the fluid, the coolant in your car, but that's done every 100,000 miles. And the same thing for heating systems at home, right? Those systems are run all the time, and they're sealed off. So we've really focused on trying to minimize the amount of service that's really required with these systems. The whole point here is that the less the user is interacting with the chiller, the more they are spending time with the instrument where they're really getting paid to do their work, right?
Right.
Greg, the semi-closed thing, that's on the return side? You're saying like on the return side, unless there's pressure, the valves stay closed, so the still water doesn't go in as much?
Yeah, it's actually in the the reservoir itself. So just like your car has a radiator cap on it that's at the low point of the system in terms of pressure, and so it would allow the pressure to build up to a couple of psi. I think it's 5 psi or something like that. I think your car is somewhere around that, and so and the system's been designed with a small air pocket on the top so that it would only vent air. The automobile,
so it's like a positive pressure, like a clean room in a way. It's a little too much to describe it, but
almost. You got it.
Well, Greg, you brought up fluid a bunch of times there, and maybe it's a good time to ask you what types of fluid does a chiller require? Like, what about compatibility there?
Yeah, so water is generally the answer, but single distilled water is probably the best thing that can be used. So from a thermal perspective, water is very hard to beat. Oftentimes, companies or users will use some type of glycol mixture in with the water, either an ethylene glycol, propylene glycol. This is often done for material compatibility. So if they're using an aluminum cold plate, say, so that we take a little bit of a hit on the thermal side of the fluid, but we get some corrosion protection. We also get some, the freezing point depression. So instead of freezing at 32, we can lower that down a little bit if they want to operate at a lower temperature. So those are the main ones. I would say either a water or water glycol mix. There's a number of other chemicals out there made by Dow that are specific to heat transfer fluids, but they're all generally glycol water-based systems.
Yeah, and there's also some like floor inert type liquids, right? Mm-hmm. So those are designed to not mess with any electronics if there is a leak, unlike water, which will fry everything. So a lot of these floor inert liquids are used in like server rooms or high power computing.
Yeah, you see that a lot. So floor inert is a dielectric, so it's not doesn't conduct electricity, and so it's used in the semiconductor world, especially if there's say connections that are made, quick disconnects that might have a drip that comes out of them, and they don't want it to land on the electronics. But you got to be careful with that in terms of compatibility on the chiller side. There's a lot of material compatibility issues with floor inert that you just need to be aware of.
So what about filters, right? Are the filters built in? How does that work?
Yeah, it's very chiller specific. And in a chiller, we're concerned with small passages where the fluid's going through, often in heat exchangers and in pumps. So depending upon the pump technology, centrifugal pumps and regenerative turbine pumps can pass larger particles than like a graphite vein pump. Those, if particles get in there, can crack the veins. So heat exchangers are pretty good about passing particles. So we're really concerned with protecting the pump in the chiller. Now, oftentimes customers have equipment or components on their side they're looking to protect as well. So this is a kind of an age-long debate. Where does the filter go? Does it go on the outlet of the chiller or the inlet? What are we trying to protect? And so oftentimes it's OEM specific, in terms of what they want to do. But particle filters are always good. Usually about 5 micron is what tends to be used. And it's especially good at startup, right? Because we've got all of these hoses or pipes that have never seen liquid going through them, right? And who knows if they've been capped off since they've been manufactured, and they've got dust and all kinds of things that are in it. And so at least on startup, we want to be able to filter all of that out. And then what tends to happen is you change your filter right after startup, and then maybe every 6 months after. But it's as long as the pump, as long as it's not preventing flow and causing high pressures for the pump to put out a filter is always recommended.
All right. So lastly, I was wondering if you guys could talk a little bit about the relationship between Sager and Laird and how you guys are working together to solve some of these problems that are in the marketplace right now.
Sure. Yeah. So, I mean, I help customers with all of the thermal products that the Sager line card. So I see air cooling, I see liquid cooling, and all of that. And for chillers, Laird is really a leading brand. And so if it's anywhere close to that, I'm helping them with sizing the right chiller, some of the initial work, and then handing it over to Greg if it's something super specific, super accurate that customers may want to do. And then we stock those chillers as well ourselves, so customers can grab it right off of our shelves.
Is there anything you'd like to add, Greg?
No, it's Vineet, I think it's covered it. It's it's really all over the place in terms of what customers need in terms of assistance when they come to us. And so the more people we have that we can throw at it, the better, right? Some customers don't know what their thermal requirements are. And so they might need to speak with Vineet or speak with an applications engineer to help them walk through some of the steps they can take to try to figure out what their requirements are and what the best solution is for their thermal needs.
And you mentioned how you're dealing with customers who are working with all different types of cooling. So I mean, at what point do you kind of transition them in their thinking to liquid cooling?
Yeah, it's really unless I know the product well, and unless there are times when the customer says, I don't want to go to liquid cooling, here's what I have. And then, it's me helping them figure out, like, it's okay, here's what we can do liquid cooling. But a lot of times it's very, very clear that it's, always liquid cooling or always air cooling. And so that doesn't come up as often, for sure. Okay. But for customers who are in that kind of boundary, it's okay. The water's warm. We definitely, or the water's cool actually, and we can definitely help them figure that out.
Well, thank you guys for joining us today. It was a great conversation.
Greg, Vineet, can you let everybody know where they can learn more about Laird's liquid cooling products?
Yeah, so the best resource is always the website. So we have a number of applications notes that talk about the different uses of our products for liquid cooling. So they really get into the specific applications, whether it be a laser, a piece of analytical equipment, medical equipment. And then there's also all the product data sheets and information on the product series. They're all available. And there's also sizing tools to help you select what the right product is for your application. So by putting in different heat inputs and the fluids you want to use and set points, it gets you to the right solution.
Awesome.
Thank you, everyone, for joining us today. Yes.
Yeah, my pleasure.
Of course.